In a 3-wire, 240-volt single-phase system, we have 3 conductors. Firstly, 2 hot conductors, referred to as line 1 and line 2. Secondly, 1 neutral conductor. It is crucial to understand the phase relationship between line 1 and line 2. They are not 180 degrees out of phase. Instead, they are typically 120 degrees apart. This means when line 1 is at 0 volts, line 2 is at 120 volts and vice versa. The neutral conductor provides a return path for the current. Now let's discuss the neutral current. In a balanced system, when the electrical load is evenly distributed between the 2 hot conductors, the current in the neutral conductor ideally becomes 0. This happens because the currents in the 2 hot conductors effectively cancel each other out. Let us distinguish this system from a split-phase circuit. A split-phase circuit is also a single-phase system, but it utilizes 2 hot conductors that are precisely 180 degrees out of phase. This is the key difference from the 3-wire, 240-volt system, where the 2 hot conductors are 120 degrees apart. Therefore, in a standard 3-wire, 240-volt system, the neutral conductor is not intended to create a split-phase circuit. The 2 hot conductors, line 1 and line 2, work together to supply the required voltage to the load. It is understandable why confusion might arise from the term opposing. While it is true that the 2 hot conductors exhibit opposite polarities, it is inaccurate to say they are completely opposing each other. Remember that they are 120 degrees apart, which facilitates the cancellation of current in the neutral conductor when the load is balanced across the 2 hot conductors. To elaborate on how the neutral current cancels out in a balanced system, let us consider a scenario. Imagine you have 2 identical 120 volts loads, one connected between line 1 and neutral, and the other connected between line 2 and neutral. If both loads draw the same current, say 10 amps, then 10 amps will flow from line 1 through the first load and back to the neutral. Similarly, 10 amps will flow from line 2 through the second load and back to the neutral. At the neutral point, these 2 currents are effectively flowing in opposite directions. Because they are equal in magnitude, they cancel each other out, resulting in 0 current in the neutral conductor. However, it is important to note that this perfect cancellation only occurs when the system is perfectly balanced. In reality, loads are rarely perfectly balanced. If one load draws more current than the other, there will be a net current flowing in the neutral conductor. For example, if the load on line 1 draws 12 amps and the load on line 2 draws 8 amps, then there will be a net current of 4 amps flowing in the neutral conductor. This neutral current is the difference between the currents in the 2 hot conductors. In practical electrical installations, it is essential to ensure that the neutral conductor is properly sized to handle any potential neutral current. Electrical codes such as the National Electrical Code, or NEC, provide guidelines for sizing neutral conductors based on the expected load and the type of circuit. For instance, NEC Table 310.15b3 and 310.15b5 address neutral conductor sizing considerations. Now let us consider what happens when the system is unbalanced. As mentioned before, an unbalanced system leads to current flowing in the neutral wire. This current can cause several issues, including increased voltage drop, overheating of the neutral conductor, and potentially even nuisance tripping of circuit breakers or ground fault circuit interrupters, or GFCIs. Excessive neutral current can also contribute to harmonic distortion in the electrical system, which can negatively impact the performance of sensitive electronic equipment. To mitigate the effects of unbalanced loads, several strategies can be employed. One approach is to distribute the loads as evenly as possible between the 2 hot conductors. This can be achieved by carefully planning the circuit layout and assigning different loads to different circuits. Another approach is to use load balancing devices, such as autotransformers or static VAR compensators, to actively balance the load on the 2 hot conductors. These devices can help to reduce the neutral current and improve the overall efficiency of the electrical system. Another important concept to understand is the voltage relationship in a 240 volts, 3-wire single-phase system. The voltage between line 1 and line 2 is 240 volts, while the voltage between line 1 and neutral and between line 2 and neutral is 120 volts. This allows for the simultaneous use of both 120 volts and 240 volts appliances and equipment. For example, a typical household might use 120 volts for lighting small appliances and electronic devices, while using 240 volts for larger appliances such as air conditioners, electric stoves, and water heaters. The 240 volts connection is achieved by connecting the appliance or equipment between line 1 and line 2, while the 120 volts connection is achieved by connecting the appliance or equipment between either line 1 or line 2 and the neutral conductor. It is important to note that the 240 volts and 120 volt circuits must be properly wired and protected by appropriate circuit breakers or fuses to prevent electrical hazards. The NEC provides detailed requirements for wiring and protection of electrical circuits, including specific requirements for 240 volts and 120 volt circuits. Understanding the difference between a 3-wire, 240 volt single-phase system and other types of electrical systems, such as 3-phase systems, is also crucial. 3-phase systems are commonly used in commercial and industrial applications where higher power levels are required. 3-phase systems use 3 hot conductors that are 120 degrees out of phase with each other, providing a more balanced and efficient power distribution compared to single-phase systems. While 3-phase systems offer several advantages, they are also more complex and require specialized equipment and expertise to install and maintain. In contrast, 3-wire, 240 volt single-phase systems are relatively simple and are commonly used in residential and small commercial applications. Another important consideration is the grounding of the electrical system. Grounding is a safety measure that helps to protect against electrical shock and fire hazards. In a properly grounded system, the neutral conductor is connected to the earth at the service entrance, providing a low impedance path for fault currents to flow back to the source. This allows circuit breakers or fuses to quickly trip and to energize the circuit in the event of a ground fault. The NEC provides detailed requirements for grounding electrical systems, including specific requirements for grounding electrodes, grounding conductors, and bonding of metallic enclosures. Proper grounding is essential for ensuring the safety and reliability of the electrical system. In summary, a 3-wire, 240 volt single-phase system consists of 2 hot conductors, line 1 and line 2, and a neutral conductor. The 2 hot conductors are 120 degrees out of phase with each other, allowing for the cancellation of current in the neutral conductor under balanced conditions. The system provides both 120 volts and 240 volts for powering various appliances and equipment. Understanding the principles of operation, including the phase relationship, neutral current, and voltage distribution, is essential for properly installing, maintaining, and troubleshooting these systems. Additionally, adhering to electrical codes such as the NEC is crucial for ensuring the safety and reliability of the electrical installation. The concepts discussed help differentiate from split-phase circuits and 3-phase systems, highlighting the unique characteristics and applications of each type of electrical system. Proper grounding techniques are paramount for safeguarding against electrical hazards and ensuring the overall safety of the electrical installation. When dealing with electrical systems, it is always recommended to consult with a qualified electrician or electrical engineer to ensure that the work is performed safely and in accordance with all applicable codes and regulations. Electrical work can be dangerous, and it is important to take all necessary precautions to prevent electrical shock, fire, and other hazards. Only qualified individuals should perform electrical work, and they should always use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. By following these guidelines, you can help to ensure the safety and reliability of electrical systems and prevent accidents. Furthermore, understanding the power factor in such a system can also be beneficial. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. In a purely resistive circuit, the power factor is 1.0, meaning that all of the power supplied is used to perform work. However, In circuits with inductive or capacitive loads, such as motors, transformers, and capacitors, the power factor can be less than 1.0. A low power factor indicates that a significant portion of the power supplied is not being used to perform work, but is instead being used to create magnetic or electric fields. This can lead to increased energy consumption, higher utility bills, and reduced system capacity. To improve power factor correction capacitors can be installed in the electrical system. These capacitors provide reactive power that cancels out the reactive power drawn by inductive loads, bringing the power factor closer to 1.0. Power factor correction can improve energy efficiency, reduce energy costs, and increase the capacity of the electrical system. The NEC provides guidelines for power factor correction in Article 460, which covers capacitors. Article 460.8 specifies the requirements for capacitor overcurrent protection, while Article 460.9 addresses capacitor disconnecting means. Understanding and addressing power factor issues can further optimize the performance and efficiency of 240 volts, 3-wire single-phase systems. Understanding the concepts of impedance and reactance can also provide a deeper understanding of how electrical systems function. Impedance is the total opposition to current flow in an alternating current or AC circuit, and it is measured in ohms. Impedance consists of two components. Firstly, resistance, which is the opposition to current flow due to the material properties of the conductor. Secondly, reactance, which is the opposition to current flow due to the presence of inductors and capacitors in the circuit. Inductive reactance is caused by the magnetic field created by an inductor, while capacitive reactance is caused by the electric field created by a capacitor. The impedance of a circuit is the vector sum of the resistance and reactance. The magnitude of the impedance determines the amount of current that will flow in the circuit for a given voltage. The phase angle between the voltage and current is determined by the relative amounts of resistance and reactance. In a purely resistive circuit, the voltage and current are in phase, while in a purely inductive circuit, the current lags the voltage by 90 degrees, and in a purely capacitive circuit, the current leads the voltage by 90 degrees. Understanding impedance and reactance is essential for analyzing and designing AC circuits, including 240 volts, 3-wire single-phase systems. By understanding the impedance of the various components in the circuit, it is possible to predict the current flow, voltage drops, and power dissipation in the circuit. This information can be used to optimize the performance and efficiency of the circuit, as well as to ensure that the circuit is properly protected against overloads and short circuits. Furthermore, it is beneficial to understand the different types of wiring methods that are commonly used in 240 volts, 3-wire single-phase systems. Some of the most common wiring methods include non-metallic sheathed cable or NM cable, electrical metallic tubing or EMT, and rigid metal conduit or RMC. NM cable, also known as Romex, is a flexible cable consisting of two or more insulated conductors enclosed in a non-metallic sheath. NM cable is commonly used for residential wiring and it is relatively easy to install. However, NM cable is not suitable for use in wet or damp locations, or in locations where it is exposed to physical damage. EMT is a thin-walled metal conduit that is used to protect electrical conductors. EMT is more durable than NM cable, and it can be used in a wider range of applications. However, EMT requires specialized tools and fittings to install, and it is more expensive than NM cable. RMC is a thick-walled metal conduit that provides the highest level of protection for electrical conductors. RMC is typically used in industrial and commercial applications where it is exposed to severe physical damage or corrosive environments. RMC is the most expensive wiring method, and it requires specialized tools and expertise to install. The NEC provides detailed requirements for the installation of different wiring methods, including specific requirements for supporting, securing, and protecting the conductors. Selecting the appropriate wiring method for a particular application depends on several factors, including the environment, the type of building construction, and the budget. By understanding the different wiring methods and their respective advantages and disadvantages, it is possible to choose the most appropriate wiring method for a particular application. Finally, it is important to understand the importance of proper overcurrent protection in 240 volts, 3-wire single-phase systems. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from damage caused by excessive current flow. Overcurrent can be caused by several factors, including overloads, short circuits, and ground faults. When an overcurrent occurs, the overcurrent protection device will trip, interrupting the flow of current and preventing damage to the circuit components. Circuit breakers are reusable overcurrent protection devices that can be reset after they trip. Fuses are single-use overcurrent protection devices that must be replaced after they blow. Circuit breakers are generally preferred over fuses, as they are more convenient to use and they provide better protection against low-level overcurrents. The NEC provides detailed requirements for overcurrent protection, including specific requirements for the size and type of overcurrent protection devices. The size of the overcurrent protection device must be matched to the ampacity of the conductors that it is protecting. The ampacity of a conductor is the maximum amount of current that the conductor can safely carry without overheating. The NEC provides tables that list the ampacities of different types of conductors based on their size, insulation type, and installation conditions. Selecting the appropriate overcurrent protection device is essential for ensuring the safety and reliability of the electrical system. By understanding the principles of overcurrent protection and the requirements of the NEC, it is possible to design and install electrical systems that are properly protected against overcurrents.